I'm going to describe Floyd-Williams priority queues. So first, what are priority queues in general? So those are data structures that have two types of operations. One is the insert, where you get an element together with a priority, and you add it to the queue. Okay. And the second operation is that you fetch, and that operation returns the element with the highest priority that is right now in the queue and removes it from the queue. Okay? So these are the two operations that the data structure needs to support, and of course we want to do it efficiently. Okay, so first a little aside, how do we store a binary tree in an array? Okay, so here is a binary tree, and we want to store it in an array starting from position 1, 2, 3, 4, and so on. Okay, so the way we do it is we just go level by level. Okay, so first we have 1, then we go on the second level 2 and 3, then we go on the third level 4, 5, 6, and 7. These are basically the positions in the table that we would use. Let's say this is position 1, then position 2, position 3, and so on. We don't use 0. Okay, so that's how we would store a binary tree. Another little aside is what are tree structured heaps. Okay, so this is basically the type of tree that we're going to use, and the property that we have for this tree is that every element, every node contains a number or a letter that must be larger or equal to the elements below it. Okay, and so on. So 14 is larger than 10, 10 is larger than 9. 8 doesn't have to be larger than 9 because even though it's in a lower level, it's not connected to 8. Okay, so now we're ready for the Floyd-Williams heap. Basically, this is a binary tree that we fill level by level, which is very natural in our array structure. So this is the last element, and every node, because it's a priority heap, has a value that is larger than the values below it. Here it's characters rather than numbers. Okay, so T is larger than Q and N is larger than F and H, and so on. Okay, so now how are we going to do insertion into a heap? Okay, so what we do is we take the new element that we're adding, in this case P, okay, and we add it to the last place open in the array, and so it automatically has a parent. Okay, and then what we do is we switch with the parent if the order is not right. So in this case we need to switch and put P here and F here. Then P is larger than N, so we need to switch P and N, so P is here and N is here, and now everything is good, so we get this final structure. Okay, so we basically have to put it at the last place, and then we call it bubble it up in order to maintain the condition that as you go down the tree things become smaller. Okay, so how do we do fetch? Well, the first part of getting the element with the highest priority is easy because that's always the root. So we simply return the root. But now we need to do something to maintain the structure of the tree. Now we have two separate trees. So what we do is we take the element that is in the last position, and we move it to the position that has just been cleared, and now we start to compare it to this element to its children. Okay, so in this case we have F, And so f is smaller both than q and then p, but q is larger, so we switch with q. So we get that f is here and q is here. And now f and f is equal to f, so that's okay, but it's smaller than g, so we need to switch between g and f. Okay, and so now we have g there and f here, and now we're done because f and e and c is okay. So now we get f, g, and q. So what we see that if we have for both operations, we basically need to go once from the top to the bottom of the tree potentially. And if the tree has n elements, then the depth of the tree is log of n. So the number of operations we need to do is log of n.